Hello, welcome to lab report number 5. Today we'll be exploring one of the fundamental concept circuits analysis, Kirchhoff's rule. This lab report will consist of Alberto Chavez, Daniel Mecheca, Cynthia Ramos Robes, Gerardo Rodriguez, and Christian Reyes. Introduction. First, Kirchhoff's current law states that the total current entering a junction is equal to the total current leaving it. This reflects the conservation of charge. Second law of Kirchhoff is the voltage law. It tells us that the sum of the voltage rises and drops around any closed loop in a circuit and must equal to zero, meaning energy isn't lost or created as charge moves through the circuit. In this lab, we measured the current and voltage across 4 different resistors and compare those values to the source voltage. By setting up loops and applying the junctions rule, we calculated percentage differences to analyze how closely our measurements match the theoretical expectations. Our goal is to understand how these rules work in practice, where differences come from, and how they minimize through more precise measurements. Let's start with the experiment setup and data collection. For the procedure plan, we have step 1, setting up the resistors as demonstrated in the lab procedure instructions and setting up the recording devices. Step 2, measuring the individual resistors and ensure the multimeter is working as well as the resistors. Step 3, setting up the circuit assembly. Step 4, setting the voltage and current to 7 volts and ensuring measurements are in milliamps for the most accurate measurements. Step 5, data collection and applying Kirchhoff's rule. And then step 6 will be our conclusion.
For this lab, we used 4 resistors, which we labeled as R1, R2, R3, and R4 using small pieces of tape, and we also used a breadboard and several connecting wires to build our circuit according to the diagram provided. To power the circuit, we used a DC power supply set to 7 volts. To take our measurements, we used a capstone interface with voltage sensors and a current sensor. The voltage sensors were connected across different resistors to measure the potential difference, and the current resistor was used to measure the current flowing through each branch of the circuit. Before building the circuit, we measured the value of each resistor using a digital multimeter to make sure we knew the exact resistances, and we also used some alligator clips and jumper cables to make all the electrical connections more secure. And finally, we used a tape and a marker to label the resistors clearly, which helped us keep track of each one during the data collection.
So for this experiment, it took us a while to figure out what the application what to use to record our results, and just being able to set it up with the resistors. But finally, we got it. We were able to do resistor 1 at first, which I'm pretty sure is what's shown. And you can see where our source is being plugged into. For resistor 1, what we basically got, we were trying to find our voltage and our current for every single resistor up to resistor 4. Resistor 1, we got 0.39 voltage, with the current being 16.5 milliamps. Resistor 2, we got 0.14 volts, and our current for that would be 6.9 milliamps. Resistor 3, we got, it jumped up actually quite a bit, and it went up to 1.78 volts, and our current stayed the same at 6.9 milliamps. In the video shown, you can see how we're going to go through the next resistor, as we're trying to figure out if it's the correct way to display it, and if our source would make sense once we do have it plugged in. For resistor 4, and then we got 6.39, I believe, voltage, and our current will be 17 milliamps, about there. And then what we have for our component, which is the source, would be 7 volts, and the current would be negative 1.1 milliamps.
Okay, so I did something wrong for sure.
Oh, wow.
Yes.
And this part of the video is where you do see our, I believe it's resistor 3 or 4. I think this is 4 actually. So our final one, which I just said before. Obviously it says negative 17 and negative 6 for our current and voltage. Doesn't matter too much. I mean, that's just what we recorded, but obviously we put it in positive values. And then there you can see displayed how we connect the resistors with our source and how it goes through.
Can you create another loop? Yes, it is entirely possible to create another loop within the circuit. By definition, a loop is any closed conducting path that begins and ends at the same node, allowing current to circulate through the components along that route. For example, if the initial loops analyzed were loop 1, which consisted of R1 and R2 in one path, and loop 2, which consisted of R2 and R3 in another, an additional loop could be formed that includes R2, R3, and R4. As long as the loop forms a closed path, Kirchhoff's loop rule can be applied. Where did the differences come from? The differences observed between the theoretical calculations and the experimental results likely came from practical sources of error that are found in real-world measurements. Resistors have manufacturing tolerances that cause their actual resistance to differ slightly from the nominal value. Wires, clips, and breadboards introduce small contact resistances that affect current flow, and measurement instruments also have precision limits that lead to rounding errors or minor fluctuations in readings, such as the multimeter. Together, all these factors can contribute to measurable variations between ideal predictions and experimental outcomes. Can you minimize these differences? Why or why not? While these differences can be reduced, it is nearly impossible for them to be completely eliminated due to physical limitations. One way to minimize them would be through using high-precision resistors with stricter tolerance ratings to improve accuracy. Further, ensuring that all connections are clean and secure will help reduce unwanted contact resistance. Calibration of measurement instruments before use can also prevent systematic errors, and maintaining a stable power supply allows the circuit to reach equilibrium before data is recorded. Despite all these efforts, however, no experimental setup can achieve perfect accuracy because every component exhibits some degree of imperfection. Therefore, small differences between theoretical and experimental results can safely always be expected.
I'm going to be doing the data analysis. So, as it shows with the capacitor lab notes, what we've noticed with the dielectric materials, for instance, is that the paper and the plastic material have very similar corrected capacitance along with their dielectric constants. What we've noticed and realized is the reason for that is because they're roughly the same thickness / distance in millimeters, matching in 3 millimeters. However, with cardboard, naturally, with a higher distance, there's going to be a lower dielectric constant because of that. And then, moving on to the theoretical and experimental comparison, because of the combined materials from paper and plastic, it's shown that it's quite a hefty difference, with one of the theoretical percent errors being up to 7%, while the other is just a simple 2%. So what we've noticed is that the type of material does make a big impact in that sense, as even shown in the first step of our lab report with a theoretical capacitance calculation, where even by adjusting the distance ever so slightly, the percent error fluctuates because of the corrected and the measure systematic errors.
In conclusion, this experiment helped us understand and confirm Kirchhoff's rules, both the junction rule and the loop rule. By measuring the current and voltage in each part of the circuit, we saw that the total current entering a junction was equal to the total current leaving it. We also verified that the sum of the voltage drops in a closed loop was equal to the total voltage supplied by the power source, which supports the loop rule. Even though there were small differences between our theoretical and experimental values, this could be explained by instrument precision, wire resistance, or connection errors during setup. Overall, the lab showed that Kirchhoff's rules are valid and very useful for analyzing complex circuits, and it also helped us practice building circuits using sensors and interpreting data accurately through Capstone.